All right, welcome everyone to RLEM23. I'm Zoltan Nagy. I'm have the pleasure to chair this session for the fourth time or this workshop. We have a great program. I'll show a few slides to get us, kick us off for this presentation or for this workshop, and I'll hand over very quickly to our main speakers today. So welcome again. Let's see. Just so you know, obviously there's more people involved here, mainly June also helping with organizing paper reviews and a lot of smart people helping review the papers to put the conference or the workshop together. Why we're doing this is this started as an idea at BuildSys 2019. I remember talking to a few folks that there were a lot of people's papers started coming out using RL in many different communities, mainly in computer science, but also in building engineering. And only very few made it into the main conferences because they were high select. And so we would try to create an outlet over the years where we could come and discuss this topic a little bit more in detail. And over the years, and they all recorded, by the way, so you can go back on YouTube and find the previous years. And the discussions have moved into practical approaches of RL in buildings. I think that's very interesting and providing a good bridge to the more academic discussions, which are also needed. But this is an outlet where we can talk about implementations also often and what are the practical challenges. And I think our two keynotes today are also reflective of that, of what are the challenges and when we do this in reality, in real buildings, and how can we make it happen. So very excited to continue this workshop in this forum. The reason I'd like to do it in virtually all is because it's, to be honest, a lot easier to organize than an in-person workshop. It's a lot easier to get people connected from all over the world. So hopefully you appreciate it. And then we'll meet on other places and other times in person, and we can high-five each other then and have a coffee. Again, it's a fourth edition. Like I said, we started in Tokyo or in Japan 4 years ago, and then Coimbra in Portugal and Boston, and then now in Istanbul / virtual to continue this tradition. The plan for today, so we have two paper sessions starting about now. There are two technical sessions, each with a keynote and a couple of technical papers. And then afterwards, so that will end the workshop effectively after the second session. And then we have two tutorials for those that are interested that will run into breakout rooms. One, Bob Test. If you followed Bob Test, fantastic outlet or program to do advanced control. And then also City-Learn that's been used a while now in many different applications. And so if you wanted to get started and continued with these topics, I'll invite you to join in. These are all self-guided, presented Jupyter notebooks, how you get started, or if you have questions to the authors, you can hunt them down there and talk to them at that point. All right, that's it, I think, from me. Exactly. So I'll stop the sharing, or you can keep me up. How do I stop? Oh, here we go. Stop sharing. And I'll hand it over to Hartmut, who will chair the first session. Thank you, Hartmut. Take it away.
Okay, thank you, Zoltan. Thank you very much. My name is Hartmut Schmeck. I'm a retired professor at Karlsruhe Institute of Technology, and I'm a distinguished senior fellow and also still active at the Research Center for Information Technology at Karlsruhe. And it's a pleasure for me to chair this first session. And the first speaker, the first invited speaker giving the first keynote is Bharathan Balaji. He's a senior applied scientist at Amazon. He got his PhD at the University of California at San Diego. His interests are mainly on machine learning, smart buildings, Internet of Things, and sustainability. And he's working at Amazon and has been working there for at least 5 years. And he addresses global challenges as waste reduction, education, automation, and certainly energy management in buildings, districts, cities, and so on. And he will give us a talk on deploying reinforcement learning for energy management at scale. And as far as I understood the program, this talk will also be based on a joint paper with some of his co-workers on economizer optimization with reinforcement learning in industry perspective. So I'm looking forward to your talk. Just go ahead, please.
Thank you, Professor. Let me share my screen. Are you all seeing the screen? All right, great.
Yes.
So thank you for introducing, inviting me to here for giving the talk. A lot of the work was done while I was at UCSD and UCLA as a PhD and postdoc, and I've continued collaborating with them. And the paper in collaboration with my Amazon colleagues is included here as well. So let's start with something basic. Why do we want to manage energy in the first place? Buildings are actually a pretty big consumer of energy. Most of the people at this workshop already know that. The energy is going to continue increasing as more and more countries industrialize, and reducing this energy is a big challenge. Renewables are a good solution. They are being adopted at a really rapid pace, but the demand is also increasing, and the intermittency of renewables is not an easy problem to solve. Energy storage is really expensive to deploy at scale today, even though the solar and wind costs are coming down rapidly. So in order for us to meet the net zero goals for 2050, net zero carbon goals set by the Paris Agreement and various other corporations, an International Energy Agency estimates we need to make buildings at least 30% more efficient to accomplish these goals. So energy management is the solution to that problem, and reinforcement learning could be a good fit here. But why is it a good fit? As most of you probably know about RL, it's a form of machine learning where an agent interacts with an environment and through trial and error learns the sequence of actions that maximizes the long-term reward. And if we use this for energy management, it can learn to do long-term decision-making in an automated manner by repeated interaction with buildings and the grid. CityLearn is a great example where the buildings are being optimized not only individually, but together with the grid for the overall energy management. RL can take in lots of data. So modern building systems that are deployed today don't even take weather forecast into account. And we are talking about all kinds of externalities like carbon price, changing electricity grid conditions, and these can be reacted to and even predicted through reinforcement learning, and that's a really big plus. And finally, a lot of the complicated part of the learning comes during training time during reinforcement learning, and the real-time deployment is fairly straightforward because all you do is run inference on neural network, and that can be deployed in real time in many of these systems. So with all these pluses, why is reinforcement learning solutions not being adopted at a wide scale? That's the focus of this talk. And I'm going to talk about mainly two things. One is real building simulations are a challenge, and second is integrated with existing systems is somewhat of an ignored topic. And finally, lack of sensor data is I may not have time to touch on. If there is time left in my 25-minute slot, I'll cover that. But the first two I'll cover completely. So going to real building simulations, if we look at most of the research papers today, they are based on Energy Plus. This is Department of Energy sponsored, a US Department of Energy sponsored simulation system. It's been around for decades and it's considered the scientific gold standard. But if you want to take a real building of even 5 to 6 floors and 100,000 square feet, it's really challenging to create an Energy Plus simulator. You need to know all kinds of details about the building, how it was architected, the construction materials used. And even when you have all of those, which takes a lot of effort and expert input to get, you need to understand how the occupants are using that building in the real time. Is the blinds open? Are the windows open? All of those have a lot of impact on how your HVAC energy is being spent. And this is really hard. So there is a whole bunch of solutions being proposed. I'm going to go in the line of work that we have done a bit, but there's also like fast simulators being developed by other people in the community. The solution that we went to was, what if we get rid of the simulator altogether? In the online approach, what we're doing is training an RL agent against a simulator. That simulator is calibrated to the real building. Therefore, once the policy is ready, you can deploy it to the real building. Whereas in the offline reinforcement learning approach, you train the policy entirely on historical data. And because it's trained on historical data, and the historical data is representative of a historical policy that has already been in existence and considers all the safety considerations for the building, it's a much easier approach, because all the intricacies of the building is captured in that historical data. So the Markov decision process for HVAC control, and HVAC, as you know, is about half of all energy that is used in a building. That's going to be the focus of most of this reinforcement learning optimization here, is as follows. Here we are controlling a single thermal zone, and therefore the state is the thermal conditions in the room, like indoor air temperature, the amount of air being supplied, what are the outdoor conditions, and humidity, and so on. The action is to set the temperature and the airflow in that space. We are using continuous action space, but could be discretized as well. And the reward is to reduce energy use while maintaining comfort to the occupants. And we're going to deploy to the real building. I'm going to just jump to the results of the real building and then show what it takes to kind of integrate with an existing building management system. So the results are based on this kind of formulation, where we have the historical data on the left to train the batch RL or offline RL policy. The thermal comfort is represented by a regression model. So we do need to predict where, if the temperature increases by 3 degrees Celsius, how uncomfortable does the person get? And this regression model captures that. We also have a similar regression for the energy consumed in the thermal zone. So we look at all the sensor values, such as airflow and temperature, and use heat transfer equations to estimate energy use in the thermal zone. And with all of those components, we will have an offline policy that we can deploy to a real building. So we came up with our own offline policy called BCM, and compared with a whole bunch of baselines. And what we did was, like, if you look at this room number 2144, 314, 44144, they are like rooms on top of each other. So we have multiple rooms where the same policy gets deployed, but they are, because they're vertically stacked, the conditions are relatively similar. And we have vertical stacks, which is right next to each other. So they face the same side of the building and all, for other offline RL baselines. And as you can see, the main takeaway is that if you just naively take an off-the-shelf offline reinforcement learning algorithm and deploy it, it might actually give you worse results. So we need to be careful on what kind of algorithms we deploy. BCQ gave us better results. So one, if everything is normalized to the rule-based control here, so one corresponds to the existing rule-based policy, and 0.9. So BCQ is one of the standard offline RL algorithms that does better. And our algorithm is a little bit of a tweak on that, where we impose a KL divergence on the existing policy and gets us another 7% savings. And this comes at a cost of an increased thermal comfort, or thermal discomfort, I should say. And that is something we should keep an eye on. If that gets too high, then that's not going to work in real world, because people are going to complain and you have to revert back to the original system. So I'll talk a little bit on how we can do that in a future slide. But moving on with the offline RL theme, like offline RL is kind of, you take historical data and you deploy and it just works, but it's going to be much worse than training an online policy against a simulator, because online policies almost get you to optimal results, versus offline is based on all kinds of constraints you've placed on the historical data. So one way we can improve on that is to learn from the existing rule-based policy. So the historical data is capturing what is referred to as behavioral policy, but you can take the best of both the behavioral policy and the rule-based policy, which possibly includes all kinds of tweaks that our building operators have learned over the years, and combine the best of both in your offline RL policy. So this was published this year at eEnergy, and we did all of these experiments in simulation, not in the real world yet. And if we had an existing historical data of a medium reinforcement learning policy, and we combine that with the rule-based policy, we can do the best of both. And that is what we are really looking for, improving that offline RL policy. But that's not really a practical solution, because that means you already have an RL policy which has a medium performance, and we collected a lot of data with that medium performance to create this policy. The practical application is actually transferring from one building to another. So you might have spent a lot of time in an experimental building, and you have a reinforcement learning policy there with some historical data. And now you want to take those learnings and deploy in a real building, in a different building, which has its own rule-based policies. So now when you combine the best of both, that's a really good direction we can go to, because the rule-based policy learns a little bit from the reinforcement learning policy, and both get combined to get savings. And the numbers here kind of indicate that if you had just not used the transfer and used the same building's historical data, it would have gotten you about the same amount of reward. So the transfer is actually quite effective here. Another trick we can do on top of offline RL is to actually continue learning, because you are interacting with the real building, and you can tune the policy further based on the interactions you have. This is still preliminary work and under submission, so I'm going to just give you brief results and move on, where we are able to beat the existing historical data's performance by fine-tuning. And if you do naive fine-tuning, you might actually get worse results than the existing policy. So that's kind of the key takeaway here, but not diving into how we are doing it exactly. But there are several challenges to actually doing this in practice. We don't have any safety guarantees. We do enforce like thresholds on how high the set points can go and how low they can go, but that's not the entire story. You want to ensure that the equipment doesn't get damaged over time, and those sort of safety guarantees are really difficult, and I've not seen research in that direction yet. We are actually also deploying the policies and see how they work. That's may not work with real building operators. They may say, no, we don't believe you. And we need to have somewhat of an offline evaluation phase where we have all these different policies and compare them, and then pick, okay, that's the right one, and tune your hyperparameters, etc. So that offline evaluation phase is, again, something more can be done in the research community. Then there's all these classic problems with reinforcement learning or any machine learning, like how do we explain this thing to people who are operating the building? How do we debug if something goes wrong? How do we generalize to new situations? Like COVID-19 was a really good example where your distribution shift is so high that any machine learning is going to be challenging to do. So I can pause here and take some questions before moving to the next phase.
Okay, are there any questions? Point.
I would have a question, if I may. Thanks so much. I was wondering, what about model-based reinforcement learning? Because you speak a lot about model-free and offline and how it's not going to work well. So what's the problem with model-based?
Yeah, model-based is, so if we are going to the simulator-based model-based, then I kind of covered that, but model-based as in data-driven models, then distribution shift is the main focus. Like if you're going to change the conditions in that thermal environment to be far different from historical, then how do you account for distribution shift in your data-driven models? So that is a pretty big challenge and not easy to solve. We do solve that in some other context, but it's like fairly open problem when it comes to building controls to do that.
Thanks.
Okay, I'll move on. I guess somebody raised a hand. Let me take that as well.
Like on the slide, you mentioned about how do we debug or how do we evaluate? And you mentioned in the earlier part of your slides that you actually deployed a solution on the building. So could you tell us a bit on what you did there in terms of the debugging or say more sanity checks before you were able to deploy?
That's kind of why I'm raising it here, because we had control over that building and they let us experiment in that building without a lot of guardrails, and that's not going to happen in most real buildings. The most we enforced was the set point, but set points don't cross given range, and without that, thermal comfort would become really an issue. But yeah, how do we do that systematically? No clue. And that's part of the problem.
But did you have any guardrails on also the neural networks or the RL algorithms that you were using in terms of maybe monitoring some special metrics or doing something different there?
Not really. The policy learning just makes sure that it stays close to historical policy in terms of enforcing a KL divergence constraint, but that's it. And that's all offline. There's nothing happening online in terms of monitoring the policy. And that's a really good direction to pursue, because what are we looking for when to detect if the policy is going bad? And this was deployed for a week each, so it wasn't that long of a period. But it is like if you want to deploy this for a long period, then it's a challenge.
We
Okay,
take
thank
another
you.
question. David Bloom has a question, but I think we should not have too long discussion right now because you want to tell us more.
Yeah, good point. Let me keep going. So the second part is, how do we integrate with existing systems? So if we look at most building management systems today, they don't allow integration of external software. They don't adopt the state-of-the-art software engineering practices. And it's really difficult to convince them to go and say, hey, take my reinforcement learning agent and deploy in your building. You need some sort of infrastructure as shown in this figure, where the building is exposing an API where it can take in control actions, where it is providing all the sensor measurements and other kinds of set point data. And this has to be provided in a secure manner with permission controls, etc. And this is happening. So when we did this research, it was already 10 years ago, when none of the buildings we knew was doing that. But now things are getting adopted, but it still is a problem if you want to deploy to more than 5 buildings in a campus. A lot of the time they won't expose this, and at scale we need this infrastructure available. The second piece is you need to keep the occupants in the loop, and if you look at your office building, most buildings I've been to do not have any way for the occupants in the building to tell the building personnel that I'm uncomfortable, the HVAC system is not working well for me, and you have to find a phone number or something, which becomes really tedious. And that's a key part of doing these experiments. If your thermal indicator might say it's only 0.2 points, 10% worse than what it was before, but what the human feels in a particular room might be very different. And you need to have them in the loop to kind of make sure that things are okay. Another kind of piece of this interface is something we developed in the computer science building at UC San Diego, where they can control the temperature, look at what their current settings are. But we also estimate the energy usage of their local office. And this is based on the sensor readings. And we need this kind of an energy usage estimation in our systems for giving feedback to the reinforcement learning agent and also understanding if something is going wrong. So that is another piece that led to the integration of the reinforcement learning policy deployment. And the third piece is that we can't just hope to create a reinforcement learning policy and just deploy it in all kinds of buildings. Buildings are very heterogeneous, and even the kind of HVAC systems they have, the sensors they have are going to be different, and the vendors and institutional knowledge of it is also like quite a big challenge to overcome. As a solution to this, we had come up with this schema called BRIC. And what it does is represents all of the building information in a standard machine readable format. So at least you can discover what's in that building and query and then deploy your solution on top of that metadata. BRIC has been around for a while. At this point, it's getting adopted by most of the companies that I know of. A lot of startups have started using it, and that makes your life a lot easier. What does it do in a little bit more detail is if you take this toy building, which has an HVAC zone and equipment and lighting controller and so on, it converts that into a graph representation that again uses standard terminology. So API is like easy to use, and you can query the building to go deploy your own solution and develop your applications. One challenge is that you do have to take the existing unstructured metadata in a building and convert it into this structured format. And this remains an open problem. There have been papers published on doing this kind of a transfer for more than 8 years now. I think there was one last year at Belsis as well. But it still takes quite a bit of human labor to get the labels required for machine learning algorithms, and does not work at scale. If I want to deploy to my 100 building campus, I'm stuck at this point. But there's progress being made, and once we have that structured data format, then things get easier. So with all of this, we put together this economizer solution at Amazon, and that's part of this RLEM workshop, where economizer optimization is actually an easy problem, but we surprisingly found nobody has tackled that in the research community before. The economizer is using free outside air when available and reduces the amount of energy required to condition the building. The existing standards are at climate zone specific level, which is like could be hundreds to thousands of miles. Whereas if we have a reinforcement learning policy, we can develop policies which are very specific to the climate conditions, weather conditions in that building. And in this case, there is no humans in the loop. There is no occupancy. There is no equipment being turned on or off. So this is fairly easy to simulate. So we don't get stuck in this energy plus simulator world. And a simple simulator is sufficient to train the reinforcement learning policy. Finally, like we had a time step of an hour. So strictly, we don't need a reinforcement learning solution. We could just use some kind of an optimizer. But it was an easy solution because doing nonlinear optimization in real time was challenging, and deployment of that at scale is hard. So reinforcement learning was like an appropriate fit. And we can make this an MDP if we want to incorporate rewards like carbon price, which have long-term dependencies. And therefore, it's easy to make upgrades to the system. So, and we did try another nonlinear optimizer, not shown here, but it didn't do as well as the RL agent because neural networks are just awesome that way. So the deployment architecture is where all of the above things come together. So the buildings that we have, about 200 plus, are all mapped to this BRIC schema. And now we can start talking to it. So all of the information is present in the graph database. The sensor data is in time series database. We can use this combination with that physics-based simulator to train our agent. And then when you're doing inference, we can use the same information and control the set points of the economizer. This works at scale. We retrain the agent every quarter to account for drift in the conditions. And some of the things that we had to be careful about was the building operators do not trust the system. So we don't actually automatically set the set point. We go to the building management interface and tell the operators, hey, you can change the set point to this value, and that will help you save energy. And they use that to override the existing set point. Still a lot of open problems here. The standardization, as I mentioned, is still manual. Building management systems are not secure, and that security becomes a pretext to block you from doing innovation. So if we can make it secure by default, a lot of this deployment headache is reduced. And finally, earning trust is difficult. These people have been operating buildings for decades, possibly, and you come and with your fancy new solution, they don't believe you most of the time. So all of the previous steps about explainability, debuggability becomes important. I was going to stop here and make this a challenge for this community to make such deployments happen at much larger scales, and what are all the different challenges we need to face to get there. If there is time left, I can talk about the sensor data stuff, but otherwise I'll pause here for questions, and thank you for having me.
Thank you. Thank you very much for your talk. I think we have 5 minutes now for discussion. I would like to start with a just very, very short question. You talked about operator feedback. What about occupant feedback? How do they respond to the changes in operating the system based on your methods?
So the methods we have explored doesn't actually take occupants into account in the offline phase. We could use data from a system like this to do that. And even in the real-time system, we need like a feedback mechanism to collect from the people. I know people in the community have like done much better than a web interface. This is like at this point 7 years old with watches and phones, etc. But if we can do that kind of feedback collection, that's like the key bottleneck. It's very difficult to convince people to start using stuff. And once you have that, then you are golden, because now you can teach your agent and play all kinds of algorithmic tricks to incorporate that into your policy.
Okay, thank you. There's a question by Kevin.
Yeah, hi, can you hear me okay?
Yeah.
Okay, great. Very interesting talk. Thank you for the work. I wonder, could you go to slide 32 for a sec?
Yeah. This one? Next one.
I think one more ahead. Yeah.
Okay.
Okay, so am I reading this correctly, that for this economizer experiment, the RL agent reduced power consumption by about 3 BTU per hour relative to the ASHRAE standard?
Yeah, yeah.
So that's like about a 1% improvement, is that right?
Yeah. At scale, it translated to more than $100,000 is what I remember. And that makes a difference when you have like 10,000 RTUs and start deploying these.
I see. Okay, so the value is you can deploy it on many similar pieces of equipment kind of all over the world and save in that way. Is that right?
Yeah.
Okay, cool. Thank you.
Yeah, there's one question by Javier.
Hey, Baratan. Thanks for the presentation. I'm Javier Arroyo from K11. I think at some point, I think you mentioned that it's best to use simulation-based reinforcement learning compared to offline or off-policy learning. And I was wondering if you could elaborate on that, because it's a bit different to the perspective I have right now, in the sense that I think it's extremely dangerous to learn with simulation, in the sense that when you deploy later on the reinforcement learning agent, it can learn from false cues that comes from the model mismatch, and it can be catastrophic when you deploy it, right?
Yeah, totally. The simulator problem kind of forks into two. One is when you're doing reinforcement learning agents, when you're training, you're actually asking, if I do something, what will happen? And that kind of a counterfactual cannot be easily learned with just historical data. And if it's based on like physics, then you might be able to answer that question with high certainty because you know exactly deterministically what's going to happen if you change something. But things like people being in the office, that's not easy to predict. Or if some equipment is going to turn on or somebody's going to open the window or open the blinds, those are not easy to predict. So whenever you have those kinds of elements in your simulation systems, which is the case in Energy Plus, then it becomes really hard. But if you can make everything to the point where physics equations dictate the flow of what's going to happen, which is the case with this economizer system, then things get a lot more under control. So that kind of a fork is what you should be careful about when you're formulating the problem.
Right.
My opinion, at least.
Yeah. Yeah, it's a tricky one. Thanks for the answer.
Okay, David has a question.
Hi, yeah, David Blum from Lawrence Berkeley National Lab. Thanks for the nice presentation. I had a question, just to clarify, well, one clarifying question first. So the, let's see, so the next, I think it's the next slide where you have the graphic of 100,000 buildings that you applied to. Yeah, so was that deploying the economizer control to rooftop units sort of at different buildings, or was there, is this a different study from the one that you're referencing before?
Same thought, same one, just a continuation of the previous slide. Sorry, I wasn't clear.
Okay, I see. So here, okay, so that's economizer control to many buildings. And then on the previous study at UCSD, just can you describe once again, so you controlled, what did you control in that study? Were they individual VAV boxes of individual zones, or was it some higher level system level control?
Yes, it was individual VAV boxes.
Okay, so I'm curious. So at those two studies kind of are controlling specific aspects of the system kind of individually, the economizer loop in the rooftop unit, or single zones at a time VAV boxes. I'm just curious your thoughts, or if there's work being done, or just kind of I'm curious your impression on more using RL for more system level control in real buildings, and sort of maybe where the state of the art there in terms of if you have a multi-zone building and you want to control the rooftop unit to set the supply air temperature and static pressures, you know, to optimize the entire building operation. I'm just curious where that sort of control stands, if you know.
Yeah, this I have seen some papers which talk about having different agent per zone and kind of like a multi-agent system. It's as soon as you have like more than 10 thermal zones, things get out of hand. I've not seen a paper which talk about systems at that scale, but real buildings have hundreds to thousands of thermal zones potentially, and that's a real challenge, and I don't think that has been tackled. It was one of my open problem slides in my sensor portion of the talk, where if we have thousands of set points to control, which is what happens in the case of what you're talking about, how do we deploy reinforcement learning agents is not very clear. There could be some, like how in the real building, we have decentralized control. Like there is a centralized portion which kind of does local control, and then the set points kind of take care of how the local system should behave. And that kind of decentralization has not been architected with reinforcement learning to the best of my knowledge. But that would be a pretty interesting study to undertake. Some of the other challenges are things like data not being available, imperfect data, etc., which is again an open.
Yeah, I guess the difficulty is also not just the scale of like number of zones that you're controlling at one time, but also just the interactions between the zones physically that might have airflow between them. And so there's physical interactions between them, and then there's physical interactions between the system level control and the local loop control. So if you're controlling many VAV boxes, then they can influence each other in terms of how the system level. So that's a lot of a lot of sort of dynamics to take into account also for the reinforcement learning control. So that's more of why I was curious. But thanks.
Yeah, 100% correct. I think if it were an easy dynamical system, then the multi-agent system would be a multi-agent solution would just work out of the box. It's just the dynamics which makes it really hard. So totally.
And that's why we're all here, right? To try to keep moving in that direction.
Okay, I think we are over time, and so I'd like to thank our keynote speaker again, and thanks for the questions and the discussion. So just let's clap our hands virtually, and we go on, and we go on to the next presentation. It's like the first paper that is in this session is or will be presented by Gagya Gokal. Gagya is an electrical engineer. He's currently pursuing his PhD in computer science at the AI for Energy Research Group at Ghent University, that's in Belgium. And his research focuses on the application of reinforcement learning for developing data-driven controllers for residential energy management. And so the title of the talk he will present, or the paper that he will present, is Real-World Implementation of Reinforcement Learning-Based Energy Coordination for a Cluster of Households. So I'm looking forward to your talk. Go ahead.
Thank you, Professor. Can you guys see my slides?
Yes.
Okay, so going with the keynote speaker, in this work, we basically did some work on real-world deployment of a reinforcement learning-based control strategy over a group of residential buildings, and that's what I'm going to present today. But to lay the foundations a bit, we basically want to see more of demand response services coming into picture due to different things happening, but more importantly, the need for balancing services because of a lot of renewables coming into the grid. And at least from a group level, the focus of our research is on how to unlock flexibility in buildings, but specifically focusing on residential buildings because that seems to be a slightly underserved area. And in terms of the problems that we see in literature or in general applications, we see that we have some existing methods like rule-based control or MPCs that are doing their jobs well in the conventional sense of things, but going ahead in terms of exploiting flexibility, they are not so great, or they're not especially useful because they're hard to develop or they do not scale well with the number of buildings. And so that's our goal in general for the research, but also for this paper. And so while we were working around it, we collaborated with a company called Domex, which is a demand aggregator. And what they are basically doing is they're serving residential apartment buildings in Greece, and they provide them energy, but they also want to be able to use some flexibility from this building to help the system operator. And so in this work, we were focusing on a similar scenario where we have a demand aggregator that can control a group of buildings, and the objective would be, in normal scenarios, just continue serving them or providing them with energy, but then also during need or whenever the system operator sends you a tracking signal, try to manage the energy consumption of this entire cluster to closely follow this tracking signal. And that basically entails coordinating the heating of different houses that you have, or different houses for which you're providing energy, but at the same time try and ensure some user comfort so that you're not basically treating your users badly in some way. And we went ahead with this problem, and to tackle this problem, we have a two-step control method. Basically, it's a hierarchical control scheme where we have a ranking system that would use data from different apartments, and then a simple dispatching mechanism that would use a PI controller and the ranks that we get to basically determine what households need to deviate from their existing control action or their existing energy behavior so as to properly track the signal that our system operator has sent. And well, the first step in this process is the RL-based ranking, where we are using a policy evaluation method to identify or to learn queue functions from existing data that we get from these apartment buildings. Now, this queue function could be learned by some simple batch reinforcement learning algorithms such as FQI. And once we have these queue functions built up, we go ahead with identifying the advantage values. So we would have a baseline policy for each of the households, which is the control action that would have happened right now. And what we want to find out is what is the value or what is the advantage of taking a different action at this moment, because we want, or the demand aggregator wants to identify which houses are willing to deviate from their business as usual and help the demand aggregator to actually track the signal. And that's where we have this advantage function that you see on the slide that would help us do that job. And once we have such advantage functions for all the households in our portfolio, we can come up with a ranking table and the PI controller can go through these houses. So the PI controller can essentially look at the ranks and dispatch houses with a lower rank first, keep a track of signal in a closed loop form, and continue this process. And the whole idea is that whatever deviation strategy we come up with through this method is in some way a least cost deviation strategy. So whatever excess amount the users would need to pay because of being a part of this is not too high. So that was the method that we went ahead with or we implemented. And this method was implemented in a real world case study. So we had about 8 apartments in Greece during this year, so February 2023, for about a month. And for each of these apartments, we basically had a on-off control scheme. So we wanted to keep things a bit more simpler. So just having a binary action set, along with which we also had some user-defined temperature set points that were fully controlled by the user and determined what the room temperature should be inside each of these households. And the constraint was that we should try and be as close to these set points as possible with a ±1 degree band for flexibility. And in terms of the data aspects, we had 1 minute logging and we had created a solution in-house through Python and the Kubernetes deployment. Now, coming to the control strategies that were there, we first had a business as usual control that would be going throughout the duration of the experiment, which is a simple rule-based policy that can take actions every 15 minutes. And then we emulated the tracking signal from the system operator. And when this tracking signal was sent to the demand aggregator, the RL-based coordinator would switch on, which would basically start with calculating the advantage values for each of the household using the queue networks that were trained over 1 month of historical data. And then the PI controller can take actions on a 1 minute level. So it is a bit more useful in that closed loop sense of things. Along with this setup, we also had nightly retraining so that we could use data which is the latest data, so to speak, but still have a 1 minute window because yeah, we wanted to check if we can work with limited data sets or not. So this was more or less the case study that we went ahead with. And the objective here was to identify if we can actually track this DR signal or not, but also to make sure that the ranking that we are coming up with that makes sense and it is learning something useful and it's not just a random ranking. And the results, a snapshot of the results that we present. This is the result for the aggregate power over the 8 households. So we wanted to measure the tracking performance or how well does the coordination strategy track this TR signal. What you see in red is the target values that were given, and the black is the observed power with the shaded areas showing the standard deviations for different observations that we had over the trial period. So that's about 1 month in February. And on the right hand side, you see a typical ranking table that is a byproduct of the RL based ranking method, where each house that we had has an action which is the deviation action. So the action other than the one that the house would have taken at the moment. We come up with a value which is the advantage value, and then we rank them in an ascending order so that the PI controller can dispatch them based on the current power level that are there for the entire cluster and the target value that's there. So this was the experiment setup that we had and the results. We also performed some analysis on the Q values that we were learning, or the outcomes of the Q network that were trained, which are there in the paper. But in all, the conclusions of this work were basically two main results. One was we could actually see that the tracking behavior was okay as compared to the number of houses that we had. Since we just had 8 houses, it wasn't an exact tracking performance, but it was still satisfactory in nature. And the second important thing was that the RL based rankings that we were coming up with had useful behavioral patterns, where we could clearly see that the Q networks were learning about the set points that the users had set. And so the rankings that we got were in some way reflecting how these set points would evolve in the future. And this was something important because through this we were able to, one, demonstrate that okay, this proof of study is working, and so now we can actually try and scale up the study in the sense of using more households. I think in the keynote as well, Bharatan mentioned that being able to deploy it on a lot more number of buildings or households would be something interesting, and we can now go ahead and try and convince collaborators to actually help us with such a thing. But also we plan to increase the duration of the study and have a bit more analysis in terms of how would it behave over an entire winter or over an entire heating period. So these were the main conclusions. I think I'm in time, so that's also the last slide that I have. Thank you for listening, and if you have any questions.
Okay, thank you very much for your talk. And questions. So I see 2 hands, Zoltan.
Yeah, thank you, Gargiev. Very cool presentation. So I understand this correctly, you implemented this in real homes.
Yeah.
Can you, so based on what we discussed before with Bharat, how did you get access to these homes? Is the first part of the question. And the second part is, did you get any feedback from the people on liking, not liking, trying to kick you out because you're messing everything up, or not seeing any impact on their lives, basically?
So to answer the first question, as a part of the projects that are funding my PhD, we collaborated with this company called Domex, which is a demand aggregator. And because they were a part of this project as well, we were able to set this field trial up because they were interested in this solution as well. And so we could get access to about 8 such households, because that's the maximum number of people that they could convince to actually allow us to do such a thing. And to answer the second part of the question, we did have some user feedback, not the kind that we would be able to work with, but we did encounter issues where people would just switch us off in between the study because they didn't like the actions that we were sending, or they thought that we were messing around with the system. And so we were basically monitoring on, are we online in all the houses or not? And whenever we used to see some discrepancies there, we could contact the company, and then they would contact the users and give us some information on, okay, what happened, or why did this person just switch us off. So there was some feedback, but not complete.
Thank you.
Okay.
There's one more question from Muhammad.
Hi, Gargia.
Hi.
Muhammad, thank you for the presentation. I have a question about the RL-based coordination, which you mentioned the control step was 1 minute action. So I was just wondering, do you think that's a lot of high resolution when we talk about control step? Because 15 minutes time step, which was the control action step of the rule-based control, I think that is more practical in terms of heat pump switching and whatever device you're controlling. So I was just wondering, how did you define that? And then second is, when the ranking is high, if I understood it correctly, does that mean that the cost of changing is low, or is it the other way around?
So to answer your second question first, if the rank is high, it would mean that this particular household would have a higher cost in terms of switching on. For example, in this particular case, for example, house 34 would be less willing to switch on as compared to the off state that it is currently in, and the high value kind of suggests that.
So would
And
you recommend, would you prefer to have
a
that
lower
house
value.
change?
No, so the idea would be to first switch on houses with a lower value. So in this case, the top 3 or 4
Yeah,
houses.
yeah, okay, makes sense. Yeah.
And in terms of the control action, it is not switching on and off the heat pumps of the houses, but it is to determine when the PI controller would look for more houses to deviate from, because in this particular step, the PI controller needs to go through the number of houses that you have. So it would start off with just switching on one house, seeing if the excess power that we have is sufficient for the tracking signal or not. And if it sees that, okay, there is still a big error, then it would try to include more houses in the dispatch. And so
Okay.
that 1 minute thing would be more useful as compared to a 15-minute control frequency that we would use for RL.
So it's more for estimating
Yeah,
rather than.
also the control is more on a higher level where it's determining which houses from the cluster to switch from, whereas the rule-based policy is more on a lower level, which is purely for a particular house.
Okay, thank you.
Okay, if you have a very short question, Kevin, then we can accept it. Otherwise, but just
It's short, yes.
very short.
Did you measure temperatures in the homes? And if so, how did they look?
Well, in a lot of homes, these temperatures were relatively flat, but they did have certain patterns in terms of slightly lower temperature set point and lower temperature values during the morning period when we guessed that most of our users went out for work, and then more comfortable temperature values around 21 degrees when they came back around 5 or 6. So we had these regular patterns, but besides these two patterns, the internal variations were not so much.
Thank you.
Okay, thank you very much again.
Thank you.
So we come to the final talk in this session. It will be presented by Matic Pokhorn. He is a master's student at the Faculty of Mathematics and Physics at the University of Ljubljana. In the web, I also saw the name of the Joseph Stefan Institute at Ljubljana. And his research interests are reinforcement learning, weather forecast post-processing, and computational topology. And he will give us a talk on smart home energy cost minimization using energy trading with deep reinforcement learning. So please go ahead.
Hi, can you hear me?
Yes.
Okay, perfect. So I'm going to present this paper called Smart Home Energy Cost Minimization using Energy Trading with Deep Reinforcement Learning, which I wrote with my colleagues. Sorry about that. Okay, so what was the motivation behind the writing of this paper? So in recent years, we have seen increased adoption of dynamic electricity pricing for residential consumers. And this gives an opportunity for smart home owners to reduce electricity costs by trading with the external energy grid. The use of deep reinforcement learning has proven as a reliable method in dynamic environments, which is why we chose to use that. And we have witnessed a lack of research in single household energy management without exploitation of applied scheduling and HVAC management. So we are not managing HVAC, and we are focusing on a single household. So the problem you can see on the screen, this is the system model. So we have an energy generation unit. The house, the smart house is consuming energy, which is fixed. We cannot control that. And then we have an energy storage system, such as a battery, with some specifications like input and output efficiency and maximum charging and discharging power. And then we are also connected to the energy grid, and we can sell and buy energy by some price. So the bought energy is usually higher than the selling energy due to some distribution system operator costs or something like that. And our objective is to minimize the cumulative cost. We can see on this below equation what is our goal. So what contributions do we make? So we are designing a deep reinforcement learning algorithm that is able to trade energy with the external electric grid. And we do this for a single household with battery storage and energy generation units. We are prioritizing comfort and habits, so we are not changing the consumption in any way. And our proposed solution therefore avoids controlling, scheduling household appliances and HVAC systems. We are able to produce savings of up to 47.66% compared to baseline policies. What consists our proposed solution? So we use the DRL algorithm we are using is TPQ network, which is designed by DeepMind, using 2 fully connected layers with 8 neurons and a relay activation function. Our state design is a sliding window for the past 48 hours with information about the household energy generation, energy consumption, battery state of charge, energy price, and the cost we have paid at every time step. So our action space, we have designed 4 actions. The first action prioritizes buying energy from the grid to charge the battery. So this is, and also the household. So this is meant for situations where price is low. So we try to make gains this way. The second action uses energy from the battery to power the house and to sell energy to the grid. This is in situations where price is high, so we are able to make profit using that. The third just buys energy from the grid and powers the house and ignores the battery altogether. And the fourth one tries to use firstly the battery to power the home. Our reward function consists of 3 parts. The first part penalizes the agent if the state of charge is near 0 or near capacity. This is so that we try to keep the agent to have the battery state of charge in kind of like a state where it's not completely empty and completely full, so we can use all the actions possible. The second part considers charging trend versus price trend. So if the battery is filling up and the price is high, then this is not a good policy, so it penalizes the agent, and it does so vice versa in all circumstances. And the third part includes the actual cost, which is our initial minimization goal. And in this graph, we can see kind of the behavior of the reward. So if the battery becomes, the state of charge becomes too low, it's going to get a high penalty, and therefore try to keep the state of charging some kind of balance. What kind of environment are we in? So for our simulations, we used measurements from a smart home in Thessaloniki in Greece on 15-minute intervals between October 2018 and October 2020. This data includes energy consumption, photovoltaic energy generation and real-time pricing energy price. We also use time of use pricing, which we appropriate based on RTP. So the mean of RTP is the same as the mean of TOU, and then we choose some offsets to create three pricing blocks. So on peak, off peak, and mid peak, which you can see on this below graph. So you have both pricing functions for kind of like a period of 3 days. As a training set, we use the period between October 2018 and October 2019. And for the test set, we use the part of the data set, which is between October 2019 and 2020. And so we create our buying price by multiplying the actual price by 2, and we create our selling price by dividing the actual price by 2. Which were our baseline policies. So we compared our model to these two. Baseline 1 we call the greedy policy, which only considers house with photovoltaic power plants, but no battery storage. So it sells its energy immediately because it has nowhere to store it. And baseline 2, which is the alternating baseline, which uses the same actions as the DRL agent, but it just cycles through them. So it goes action 1, action 2, action 3, action 4, and so on. So this is the part of the test set. So the above graph shows us the cumulative cost over time. And the blue line is our proposed solution. So you can see how gradually our agent is making gains in such a way that the cumulative cost is lower than the baseline policies. And below we can see the RTP market price. So here are the actual results. So on the y-axis we can see cumulative cost, and the blue bar plots are 2 instances of our DRL agent. And we also have some different battery specifications, such as capacity, efficiency, and input and output power. And we can see in all instances, our solutions are better than both baselines. And we are looking at a graph for the RTP market price. And in the next result slide, you can see the same for the TOU market price. So the results are the same, kind of similar for both pricing policies. And our agent is able to reduce the cost in all circumstances, by circumstances I mean battery specifications. One additional benefit of our solution is self-balancing, and in the case that you can see on the screen on these graphs, our algorithm deems it smart to just initially store energy as opposed to selling it, which is the light green color. So the y-axis here is the generated energy of the PV power plant, and the colored parts are the amounts of energy that it sends to different units in the system. Here, so once the battery is full, it then proceeds to sell the leftover energy back to the grid. And here on the right, you can see baseline 2, which is, I mean, this baseline doesn't learn anything, it just goes through it randomly. And our solution can do it smartly, of course. So to conclude and provide some info on our future work, we investigated the energy cost minimization problem in smart homes, and we solved it using deep reinforcement learning, particularly with the DQN algorithm. And we were able to produce savings of up to 47.66% compared to our design baselines. And in the future, we are planning to give a multi-agent approach So we will create kind of in our simulations, we'll create a community of homes that are able to trade with one another and also interact with the external energy grid. And that's how we are going to try to minimize the whole community's electricity cost. And we will also try using some other deep reinforcement learning algorithms, such as deep deterministic policy gradient, in order to have the option to have like a continuous action space. Because now we are only using like UKM, we are using a discrete action space. And for that, this would be all. So thank you for your attention. If you have like any follow-up questions, you can ask them. But otherwise, here is my email is available and our project GitHub link. So yeah, thanks.
Okay, thank you very much. Maybe we can have one question. Okay, there's a question by Chris.
Thanks for the nice presentation. One clarifying question and then a more conceptual one. The first is, if I understand correctly, for your state, you're considering PV generation. If I'm correct, you don't use any, let's say, forecast of the PV generation, which is weather dependent, of course. Is that the case?
Yeah, that's right. That's right. We're not using any forecasting here.
Yeah, so probably you could do a bit better even if you have that, but yeah, that's fine. But then for your baselines, if you, when you were showing how the RL performance was mainly charging the battery until noon-ish, and then after the, so actually the next slide where you show the one where you show what's happening with the PV power.
Mm-hmm.
Okay, yeah,
this one. So if you looked at your scheme, so it learns basically to charge until noon, presumably because prices tend to on average be cheaper in the morning as opposed to the afternoon. So looking at this, I assume there's a reasonable decision, but it also means to me that you could probably conceive as a human sort of a better baseline than the one you're using now, right? Which would be purely rule-based, something like this. If the price is below the average, then charge, otherwise do something else with your energy. Did you consider this, or would you consider this? And if so, if not, why not?
Yes, we have thought about that, but we also considered, as I said, changing battery specifications.
Mm-hmm.
And we haven't actually tested this, but if the battery efficiency, for example, becomes very, very low, then a rule-based solution isn't going to make it, because it's still going to try to use the battery. So it's very hypothetical, but we have tested this on our solution. And if the efficiency of the battery, so if the battery becomes unusable in some sense, then it's going to learn that it is unusable and it's not going to use the battery at all, which I think a rule-based solution wouldn't do.
Yeah, you may or may not. Yeah, that depends on how smart the human is deciding the rules, of course. If you know
That's
that.
true.
But anyways, yeah. But yeah, basically what I'm saying is it would be useful to use more competitive baseline. That's mainly the suggestion I would have if you consider any follow-up or basically. Thanks.
Thank you.
I think I have to stop the discussion at this point because we are over time. It's a pity really of this online setting that we cannot meet in the coffee break in between and really talk to each other and ask all the questions that have accumulated meanwhile. But I'd like to thank all the speakers for this session again. So big applause for the speakers. And we have a short break now. The original schedule is that we meet again at 20 past. Probably we say we meet at 25 past.
25.
Yeah, 25. Is that okay? Okay.
25 is good, and if you want to discuss, go ahead, or chat about questions. If things have piled up, you can still do that.
Okay. Yeah. Okay. So we continue then with the program at 8:25. Okay.
Thanks, everyone.
Thanks. See you soon.
Last talk, I was wondering at what point do we actually talk about deep learning, deep reinforcement learning? So it was 2 layers. Is that deep?
Yeah, that's a good question. Is Bharat, if you're still there, how big were your networks that you used?
They were also
Question
same,
for me, or
same
Why not?
layers.
It's a coffee question.
We just have a coffee break now.
sure.
I think the question is, does it need to be more than 2 layers? Like, where do we need more complex?
Yeah. But is everything beyond 1, is that deep? So for me, deep is something really that's must be more than 2, I would say.
So maybe we could go for 3 layers then. Yeah, it should be okay then.
Yeah.
Or maybe you could just add 1 attention layer or something. That's always like in recent years has been in the papers and stuff.
Yeah, I think the deeper the model-free approaches, right, that we looked at a lot, they will need even more data if you add even more layers, right? So you actually don't want to do that. So I think for our applications, you don't really need them a lot. I think people add them because, yeah, like Bharat said, there's more than 2, and that's it. But I don't think there has been a serious discussion on model or neural network sizes. I know we did them, and we just don't publish them because it's a boring paper. Like, oh, we tried this many different layers and whatnot, it didn't work. But those would be interesting papers to find, like do the formal setup and see how much variation do you need, and how much performance you gain, how much data you gain, how biased it gets if you don't have enough. That's definitely interesting studies that nobody seems to want to do or hasn't published, right?
Yeah. And then there's the other question was, certainly this workshop is on reinforcement learning, but there are other methods. And I usually like to compare different methods and see what is actually the comparative performance compared to probably some regression methods, or there are so many machine learning or intelligent methods. Nowadays, everything is AI, but we used to give it explicit names that were not AI. So there are different approaches. And shouldn't we also always compare the results of one method with others in order to see how relevant they actually are?
Yeah, I think and at least have kind of like what Chris said also at the end, is like we need comparisons that are fair.
Yes.
And especially for buildings, there's a lot of rules, like also what Bharat showed, like it's not robots that you train from scratch. You know pretty well what exists, some rules. Astro has tons of rules you can just use in certain notation. So those are definitely more realistic baselines, I think. It would be a very good use of our time to do that, so to speak.
Mm-hmm. I do agree with Chris on that last point, because I think the basic baseline you just mentioned is just like loading the battery until it's full and then using that later, maybe. That's just like the standard default case that any building at the moment does, right? So not including that seems a bit like comparing not against state of the art, though.
Yeah. And one of the things that... No, go ahead. Go ahead, Kevin.
Oh, okay. I stepped away for a minute, so I missed some of the discussion. I just wanted to add that that for this problem, there is an analytical optimal solution. It's a closed form policy, and it's a threshold policy. If price is above X, do Y, that sort of thing. So it might be really interesting as a follow-up to this work to compare whatever policy the RL converges to compare that to the optimal policy and see what the optimality gap is.
That seems like a work for a real computer scientist who wants to do some regret analysis or something.
Yeah. And the other thing that it keeps coming back, especially when we talk about practicality, and I know David did a lot of work on this, David Blum, he's still here, and Kevin also, and you talk about we talk about all these approaches, but they have to be implemented, right? And some have a lot of sort of offline time that you need to do, and then they're very easy at inference time, and some have a lot very easy at the offline time, but then the trickier at the implementation time, and there's just no, let's say, fair comparison. Like, I think you can make any method be superior if you pick the correct or the right KPIs for you. And but there's probably not sort of like a comprehensive, fair comparison from a practical standpoint also that it looks into how long does it take to implement this, what does it cost, and what are the gains. And then compare that to like a baseline, like that's usually done. And that would be a really good comparison, but very, very tough to do, because you would also need access to all those buildings, and that's also tough.
Yeah, I think that's a really good point, Zoltan. And like part of it is also finding the people who are experts in these domains and know what exactly to do and integrating them with the rest of the ecosystem. All quite hard.
Yeah, but
I was hoping this is all of you people, but that's okay.
And when you select houses for experiments, certainly the occupants should be normal occupants. If you just have experts, then you don't get practical results, because they are biased. They like these methods and they like to respond. And that's also the problem with field tests that we make. That, like, we have run quite a few field tests with 10, 20, even one with 300 households, and there the challenge always is to find actually the adequate people for testing our methods. Yeah? But I think we're over time again.
Chris is up.
Indeed, yeah.
So Chris will come now.
Yes. Do we have all the speakers online, maybe? So we should have John, Judah, and David.
John Sybil's online.
Okay. Yeah, okay. Okay, then I guess we can get started. So again, we have 3 talks scheduled, a keynote and then 2 more papers. So the first will be delivered by John Sybil, who's here now. And he'll be talking about whether or not an agent is better than a baseline. So that sort of connects to the discussion we were having about baselines. And he will talk about Google's experiment design for deploying control in smart buildings. John has been a tech lead and is also staff software engineer in Google Core Enterprise Machine Learning. And he's on a mission there to deploy novel fault detection and diagnostics and practical smart control to large-scale industrial problems. He leads multiple development efforts that combine multiple anomaly detection with model explainability. And he also leads a research effort to deploy reinforcement learning to make commercial office buildings more efficient and sustainable. He also has worked on other projects like dialogue summarization models for Google Chat. And apart from his task at Google, he also teaches machine learning at the George Washington University. And before joining Google, he developed and applied algorithms, statistical analysis, machine learning solutions to cybersecurity, agriculture, counterfeit detection, and missile defense. But I'll leave the floor now to John, so take it away, and let's please welcome John here.
Well, thank you, Chris. Appreciate the invitation to speak to this workshop. I think there are a lot of things that I'm certainly learning, and I hope to share a few things about what we're doing. We're currently in a stage right now where we're developing algorithms and trying various different reinforcement learning algorithms or enhancements on live buildings. And what I'll be talking to you about today is kind of our procedure, our experiment design for deploying a reinforcement learning agent on buildings for live experiments. This is very much ongoing, and I would say that our project is a work in progress. While we're making progress, we haven't achieved our goals yet, but I think we're on our way to getting there. But what's very, very important, I think, is to apply a good experimental method to any kind of live experiments like this, so that we understand and can characterize performance accurately and in a convincing way. So people will invest more in it, so they'll realize the value behind it, and so we're confident also in our results. So why do we do all of this? What's the reasoning behind all of this effort here? And it feels a little bit like I'm preaching to the choir, so to speak. But we know that there's been an increase in droughts and flooding, extreme weather events in the recent past, and scientific consensus suggests to some degree that emissions generated by humans and human processes plays a role in some of these climate events. So it makes sense, of course, for us to consider what can we do in various aspects of generating these emissions. And if we look at buildings themselves, and these are just statistics drawn for the globe, in 2022, these are statistics for 2022, there's a consumption of 135 exajoules across in operational energy demand in buildings themselves. So all buildings globally, 135 exajoules. But what's very interesting is this represents a 4% increase from 2020 and a 3% increase over the previous peak, pre-pandemic peak of 2019. Furthermore, in the world of emissions, we're also increasing our emissions, exceeding the pre-pandemic all-time high that was achieved in 2019 by 2%. For a total of 10 gigatons of CO2. So interestingly enough, as we get more information about the influence of emissions, we still tend to consume more and emit more. So there's certainly something that needs to be done. Now, what we would like to do, the goal that we have here is clearly there are aspirational goals where we have new buildings or buildings that have been retrofitted with entirely renewable sources, heat pumps, energy storage units, etc. We're really focused on achieving energy efficiency with the existing building infrastructure. Maybe not achieving full carbon neutrality, but offsetting a lot of the load from non-renewable sources to renewable sources. And we believe that we can apply and leverage AI to do that. And the key piece is, for a company like Google, we have in total north of 870 buildings. To retrofit them with entirely carbon neutral systems is a huge load. It takes enormous amount of investment and time to do that. But we would like to achieve something much more in the near term. So that's what this project is all about. And so our goal is not necessarily to take on the newest building that Google owns, but some of the more average buildings. And we want to see what we can do with the average buildings and see if we can improve upon them. And hopefully the average building becomes representative of a much larger fraction of the fleet than, say, our specialized buildings do. So we want to achieve this with optimal control. We want to simultaneously reduce carbon emission and energy consumption using optimal control and more specifically, reinforcement learning. And our research hypothesis or objective here is to reduce the energy consumption and greenhouse gas emission that are emitted through HVAC devices in commercial office buildings without compromising occupancy comfort. And we've established a minimum success criteria internally here of a minimum of 5% reduction in carbon emission, minimum of 5% reduction in energy consumption while maintaining occupant comfort conditions. So how do we get to 5%? 5% seems like a conservative number based on a lot of research has been done on simulation, but we realize that real world effects sometimes make things more difficult. And so we had to choose a slightly lower number, but still a number that if we were to achieve it could be scaled up and actually be cost effective for a company like Google. So that's essentially the choice of the 5%. And so that's the kind of our success criteria. Now that we've got that success criteria, we want to see how can we develop models that achieve that success criteria, and how can we prove that they've actually met that criteria. So if we were to kind of decompose a typical workday in one of our building offices, this is just a recording from one of our days here. It tends to look like this. We tend to have three principal electrical consumers. I'm not showing gas consumers, but we're looking at three principal electrical consumers. The air circulation, that's the blower electrical energy rate, that's shown in blue. Air conditioning electrical energy, that's shown in red. That's really driving the compressors. And then we have the pump electrical energy rate, which is circulating the water. So this was happening in the summertime, as you can probably see, based on the AC usage. And there's not a whole lot of heating necessary. So the load on the electrical pump that's circulating hot water is the smallest consumer. Now, given this kind of a profile, we would like to see how we can actually, the national question is, where can we potentially reduce energy? And we think we can do it in the following manner. So let's assume that we can just aggregate all of the electrical energy and form some sort of a curve that's shown here, like in the red line. And then what we might be able to do is achieve a curve that looks a little bit more like the green line, where we can reduce the initial load, especially on the airflow at the beginning of the day. Right now, everything gets spun up. There's a huge amount of consumption early in the morning. We think we can do a much more gradual ramp up in the morning. And then also at the end of the day, we can end the day perhaps a little bit more progressive earlier. And rather than end all of the load at once, drop all the load at once, we can gradually reduce the load over time. And then at the top, we believe that we can also, by being a little bit more efficient about how we consume our energy, we can also reduce the top of the load a little bit. So those are three areas where we can reduce energy consumption. And here's just an example of some of the devices and buildings we have in one of our office buildings. So we've got the chillers, rooftop devices, driving the refrigeration cycle here, large compressors. We have air handlers that are moving air throughout the building, circulating the air throughout the building. Maybe on the roof or in other locations, we have the hot water system that's, number one, heating the hot water with natural gas and circulating the hot water using water pumps. And then we have various meters, etc. Now, all of the buildings that we operate on are fairly well instrumented. So you'll get airflow rates, set points, pressures, temperatures, fan motor percentages. All of that is actually recorded in our digital buildings data stream and is compliant with Google's digital buildings ontology, which is available in open source. So we have a fairly rich feature set that's being generated from the exterior devices and also from the interior devices. So this is what maybe an average work area looks like at Google. Lots of open spaces here with devices like variable air volumes that circulate, move the air into the zones, and then using hot water system, The hot water cycle can provide local heating and ventilation. So that's pretty much a high-level model that exists in almost all of our building office spaces. And so we would like to now kind of take this problem, this real-world scenario, and combine that and frame it in a reinforcement learning setup. And we'll start with the basic Bartow-Sutton framing here, where we have an environment and an agent. And the environment is essentially the building and the exterior environment, weather conditions, etc. The agent is the control agent. And the environment, the building, produces a state vector in our case, every 5 minutes. Our interval is every 5 minutes. That state vector is then acted upon by the agent. The agent then chooses a particular action, alters the environment, and the environment also provides some sort of reward. So for us to convert our problem into a reinforcement learning problem, we kind of have to fill in those gaps. So let's do that here. So I mentioned that we have sensors on all of the devices. We also have an occupancy signal. And we also have information, of course, about the time of day of week, etc. And all of the devices are producing airflow rates, temperatures, CO2 levels through the digital buildings data stream through our API. The action space on the right-hand side here represent the devices that we're acting on. So we're not working at this point on individual zones or the VAVs, but we're working on the hot water system, controlling a hot water system, because that's obviously the consumer of natural gas and some electricity, and also the AC units, because they're consuming a lot of the electricity and airflow and driving the compressor for the refrigeration cycle. So we have three different types of set points for each one of these three devices. This particular building has 2 ACs and one hot water system, so you'll see 2 ACs represented here. The hot water system, as well as the ACs, have kind of a hybrid action space, which puts us into a unique situation where you have both discrete actions as well as continuous action. So, for example, you have the discrete action of turning the device on or off, and then the continuous actions of choosing water temperatures and differential pressures. So the water temperature, of course, determines how much heat you have, what the temperature difference is, the temperature gradient, and then the pressure in hot water, the differential pressure, and then in the air, the static pressure determines how much mass you move across. So those two combinations kind of give you a lot of leverage over how much energy is consumed by the building overall. Okay, so that's kind of the action framing. Then we have the reward function, which is, won't talk too much about it in this presentation, but it's a combination of how well we maintain comfort conditions, or how many occupied zones are in their set points, within their set point, within the deadband, how much cost is incurred in that last 5-minute interval using electricity, natural gas, and then also how much carbon is emitted from electrical sources as well as natural gas. And that is all wrapped up in a reward function, which is represented as a scalar. That's what we call the 3C reward: comfort, cost, and carbon reward function. And what we've done is we've established kind of a base building abstract concept. And then that base building can be represented as a simulation, so a physics-based simulation, a data-driven based emulation, or at the end, the real building. So theoretically, one could train on either the emulation or the simulation. Once one's trained, then one just simply restarts the process and connects it with the real building, and the agent will then be able to operate on that. On the agent side, we are built on TF Agents, which is a TensorFlow-based reinforcement learning library. And we use both behavior cloning and soft actor critic. And I'll talk a little bit more about this, but one of the learnings that we had was, because we need to operate on both discrete and continuous action spaces, what we've done is we've enhanced or extended soft actor critic to what we call hybrid action soft actor critic that has both the ability to operate discrete actions as well as continuous actions. This is kind of a little bit more of a complex view of our system here. We have up here our RL control agent, As I mentioned here, we have our states, reward, and actions. And these are all in kind of the normalized spaces. And the environment then masks away these three principal concepts: the reward function, which is implemented as what we call the 3C reward function, which takes in kind of the electrical pricing, gas pricing, a bunch of conversions, and then also the operator preferences or priorities, which is more important to conserve on carbon or to conserve on energy or to maintain comfort conditions. So those are some weights that are assigned to that reward function. And then, of course, we have the base building, which is then implemented as either an API that is driven internally within Google, or presumably in the future within the Google Cloud platform. And on the right-hand side, we also want to know when a building or when a zone is occupied. So we provide a zone-by-zone occupancy signal, which can be either based on things like wireless or badge readers or other items like that, sensor items like that. Or for the time being, we're using a stochastic occupancy model, which kind of represents a probability of the population arriving and departing within the buildings, that's calibrated against true building behaviors. So as we said earlier, there is the need to kind of train the agent before deploying the agent. So I'll talk briefly about how we do that. Now, I'll note that there's a little bit of a discrepancy with the previous presentation about offline training. What I mean, when I say offline, I mean very specifically, the agent is trained without interacting directly with the building, so slightly different. So previously, I think offline training meant just recorded data. Here, offline training actually includes simulation. So slight discrepancy from the previous discussion, previous keynote. So we need to train an agent obviously offline, and because training requires many iterations and the thermodynamics of the building is quite slow. So it's necessary, and certainly training putting an untrained agent on the live building is certainly a risky item and bound to make some mistakes. So we need to create some digital twins that enable this offline training. Those digital twins represent a specific building, and we have two methods of doing that. One is using a simulation where we actually have a physical model of the thermodynamics. This is not Energy Plus, and Judah will kind of describe that simulation, so I won't spend too much time on the discussion about the simulation. We also have a data-driven emulation, which is a multivariate based on a multivariate regression model. Effectively, we have an LSTM that takes the past history, most recent history, several steps in the past, and then and states and actions, and then given the current state and the agent's action predicts the next state. And we essentially wrap that in that building, abstract building concept, and the agent can learn on either the simulation or the emulation, or we hope in the future both, to achieve a good policy. And this diagram here just illustrates that. The basic emulation is essentially trained based on device logs, where we train the regression model. That regression model then can interactively train our agent, and then that trained agent can then get deployed on the device, on the cloud, and then connect to the real building via APIs. Alternatively, we can do that via simulation, where we customize the simulation, which Judah is going to explain. We customize the simulation given the parameters of the building and the devices inside the building, and that goes through a calibration phase, and that gives us a simulation that we believe is a good representation of the actual building. Either way, we can interactively train the agent. Once we have that trained agent, we can then deploy it on the real building. So most of the discussion right now is really how, once we have that agent, how do we actually get it deployed on the real building, and how do we establish whether or not the new agent is better, as equal to, or worse than the baseline control. We'll talk about that here in the next few slides. But before I go there, this is our test building here, 68,000 square feet, 137 devices. It was somewhere around 512 zones. So it's a fairly representative building, by no means our largest or most modern. but the HVAC system here is fairly well tuned by the technicians. So we wouldn't say this is a very modern building, but we also would say it's pretty well maintained. So it's running at a pretty high standard. So achieving the 5% objectives is not necessarily going to be an easy task. So with that, I would like to move the conversation towards discussing three phases we have in executing live experiments on that particular building and another set of buildings that we have lined up for future live experiments. So we have really three stages. The first is preparation and checks, where we get ready for the deployment of the agent, get it on the building. Second piece is handing control over to the agent and then monitoring it and watching its execution. And then the third is the analysis and evaluation. We look at the performance of the agent and then generate new hypotheses that lead to new ideas and designs that improve the model, and then we begin that cycle again. Then we go to the next trial. So we have this cyclic process that we've adopted at Google, fairly common, but we'll just cover a few of the details here of how we make that work. All right, so before the trial, let's talk about preparation and checks. And a lot of this is going to be very practical and just achieved, I would say, via hands-on experience and interacting with the building and with the operators and with the occupants. So hopefully some of this will be useful for others that are in the process of deploying their agents into the real world. So the first thing we found is very necessary is we need a trial procedure and protocol, very fixed procedure. We call it a method of operation that's coordinated with the facilities team, with the occupants, and with the machine learning engineers. And before we deploy the model, we need to make sure that the state vector is fully represented in the telemetry stream. That is surprisingly hard. It seems like such an obvious thing, especially if you're working in the simulated world. You always get a full state vector, but in the real world, we have things like devices go offline on a regular basis. The APIs change, the software changes, and suddenly the devices are not available. And of course, the agent requires full action spaces. And as I mentioned, agents go offline regularly. And API changes can create telemetry interruptions. In fact, right now our system isn't running because we, in fact, have an issue with some of the details in the API that runs the whole thing. So one needs to make sure also the action space is operational, and this is a little bit challenging. You can imagine that you bring the agent up online and you just observe the state and make sure all the devices are fully represented. But you also need to make sure that before you hand control over from the baseline, from the existing control to the agent control, that the agent actually can assign values to the correct set points. And we, in our procedure, that's one thing that we have is we can actually observe how the agent is generating its actions, sending that through the cloud, the internal cloud API to the actual BMS, and we can see the numbers changing on the BMS, and that's a very good pre-check to make sure that, first of all, the agent isn't doing anything completely crazy and abnormal, and secondly, that we have the full connectivity in place. And so we do this with having just essentially disabled the very last piece of what we call the ML write back to the BMS. So there's an address that we have in the BMS, a specific data address that's dedicated to machine learning, or the RL agent, and then another address which is dedicated to the baseline control. And under normal conditions, the baseline control address is what's used to change the values on the devices. But when we toggle to hand over control, we actually just read from a different address, and that is how we actually can observe that the full end-to-end is working all the way down to the BMS. And we want to make sure the agent is able to write actions to the BMS, which is what I said earlier. And this is just a view here. This is kind of the logic view of the AC, or our second AC. The others look very similar, where we have our toggles here, where the machine learning write back is enabled or disabled. And it's very easy then for the operators and that are familiar with using these toggles and these control set points to enable or disable the reinforcement learning agent.
No, John,
So,
sorry to interrupt,
yeah, go ahead.
saying you only have a few minutes left. I'm not sure how many slides you.
Yeah, I'll actually, let me go there real quick. I'll cover this piece quickly. So in monitoring execution, that's essentially transitioning from baseline control to agent control, which is very similar to what I talked about earlier. And then we can enable and disable devices. Then we observe the agent, the building under agent control. And then we want to collect over the full temperature cycle for at least a day and several days. And then if something goes south, then what we can do is hand over the building back to the original control, baseline control. Here's just an example of what our very first trial here, where the building, you can see the building, the colors here represent, green represents good temperatures and red represents alarms. And the agent decided here to shut down the ACs, and you can see that the number of alarms increased. So we had to actually prematurely disable and hand over control back to the baseline control before it got into a really bad situation. And you can see here towards the end, the building got quite in a bad situation, but was recoverable. We also have displays, dashboards to observe how the agent is acting with respect to the building, how the building is responding. And we can see exactly how much carbon is being emitted and how much energy is being consumed. All right, so to speed things up a little bit here, the next thing is after the trial, the types of analysis and evaluation. So what we do here is we evaluate how good of a effect we have, again, of the agent versus the baseline. And we want to achieve a negative value where the agent consumes less electricity, less natural gas. Similarly, we do the same thing with carbon. We want to see how well does the agent perform against the baseline, and also with comfort. And the comfort is essentially looking at how many occupied zones there are where the temperatures, the average discrepancy from the deadband for the entire building. So this essentially tells us how close we are on all the three criteria. And then the way we use a baseline is the same building under local control. Ideally, we would like to compare performance with the same building under the same ambient conditions, like you can do in a simulation. But unfortunately, in the real world, you have to choose one or the other. You have to either choose the building or the ambient conditions. And even though there are many similar buildings in the area, there are too many physical differences amongst these buildings to be able to be compared. So we essentially look for this, compare, the baseline is the same building under local control, under the rules-based control. And after the trial, we break down the results into similar ambient conditions. We do that here very briefly here. We assume that the ambient conditions for the baseline or the rules-based control before and after the trial are effectively similar or equivalent to the ones when the agent was under control. And so we break it apart by occupied versus unoccupied times, and then we aggregate into hourly sums. And then we split it into outside air temperature bins of 1 degree each. And so now we can compare what it was like at 0 degrees, at 5 degrees, et cetera. And we can compare against the different metrics. And I'll show that here. So each of these will apply a statistical test because they become different distributions. So we need a statistical test. We use the Mann-Whitney, and it's applied to each of the temperature bins. And then we summarize for each of the criterion for the average performance, with all the bins that have p-values less than 0.05 or a high confidence, 95% confidence. Something like, and it looks like something like this right here. The x-axis represents the outside air conditions, the ambient conditions, and then we can compare baseline versus agent, and we hope to see negative values here at the bottom, the percentages here. A negative percentage means that in this particular criterion, we improved. Now, in some cases, the p-values are not as high as we want. We don't have enough data points, and the distributions aren't far apart enough. So we need to collect more data. But essentially, you can now compare the distributions for equivalent conditions under baseline versus agent control. And then, as the follow-on actions, we define where the agent performed suboptimally, and we develop alternative approaches and then plan for the next cycle, for the next version. And a couple of examples of improvements from the past trials are state space reductions, essentially using histogramming, taking a vector of 1,200 features and reducing it down to about 200 features, made a significant improvement. We also did some tuning with regard to the reward function. Discrete action pre-training was another thing, learning from the baseline control and specifically applying it to the discrete action, which is the on and off for each of the devices, and then the design and implementation of the soft action, this hybrid action soft actor critic that can do both soft, continuous as well as discrete actions. And then just to summarize here, we need to have some near-term solutions. We need to be able to work with the existing building infrastructure we have. And we need to have a formal process for testing. And we believe that it makes sense to use the existing building under the existing conditions and then apply the agent against the rules-based control. And it needs to be done with preparations of checks, monitoring and execution, analysis and evaluation. And one thing that we've noticed in comparing to simulations and the live trials is that a lot of times these live trials really identify enhancements that we wouldn't have thought of had we were just looking at simulations. And also present some additional challenges like devices being offline or the environment rejecting actions. Those are real world effects that we don't often see in simulations. So in parting, I'd like to leave you with this quote from Sundar, our CEO. We believe that this is an effort along these lines here, that we want to be, Google wants to be 24/7 carbon free, carbon neutral by 2030. Whether or not we achieve 2030 is another question, but we believe this is part of the overarching goal of becoming carbon neutral. And thank you very much for your time. And if there's any time for questions, I'm happy to take them now.
Okay, thanks, John. And please join me in thanking him. Great presentation. Okay, we're running a little late, but I just want to give an opportunity to ask at least one question. I think Javier was the first one to virtually raise his hand, so please go ahead.
Thanks, John, for the presentation. It's very nice to see that there's research in Google in this field. And I was wondering, did you explore or consider other optimal control approaches like MPC, and why you disregarded it?
Well, we haven't disregarded it. We chose the reinforcement learning based approach, and principally because of the problem formulation, and that was the first approach. We're very much in the process of research, and model-based control is another alternative that we can follow. Now, we would have to use some sort of a model. We decided to do a data-driven approach, model-free approach initially. So while I say, this is a pathway along we're trying different approaches, and MPC is something that we would potentially consider in the future, but certainly not we haven't discarded or ignored it. It's something that we are looking for in the future.
Okay, great, thanks.
Thanks. Yeah, we are running late. I still see 3 hands, but I'm just going to give opportunity to one of you if it's your short question. I think Hartmut was next in line, so please shoot.
Yeah, just one question. You talk about optimal control, but how adaptive will that control actually be if you have changing operating environments? It might be the necessity to actually adapt. And just one remark to this slide. When the goal actually is to be carbon free, you have to consider the intermittency of the energy supply. And it means energy efficiency is not the major challenge, but energy flexibility is the major challenge. And that's a different topic.
To the energy flexibility, yeah, that's true. Efficiency plays a role. And clearly, this is not going to achieve this audacious goal here at 2030 entirely by itself. We see energy efficiency as one step in a much greater agenda, and energy flexibility is certainly part of that. That's not what the scope of this conversation is, however. Adaptability, that's a very good question. Clearly, the model has to be retrained periodically. That's for the environment. So given for a particular building, and we can optimize over a window of time, there's a need to continuously optimize as the external conditions change or the thermal properties of the building change. Equipment changes, layout of the building changes. So there's a need to continuously train and retrain these agents over time, and that can be automated. That's a fairly automatable process. Now, in terms of adaptability across buildings, we believe, just having studied a few of these cases, it's more efficient and effective to focus on being able to train a bespoke model for each building in an efficient way. So we don't have to take a generic building model and try to adapt it to a real building. So our current agenda here is to train models to the buildings based on either the historical data or an adapted simulation.
Okay, thank you. I'm afraid I have to close the discussion now because we're running a little late again. So please join me in thanking John again for the interesting talk, and let's move swiftly to the next one, which will be delivered by Judah Goldfeder. He'll be talking about lightweight calibrated simulation, enabling efficient offline learning for optimal control of real buildings. And Judah is a PhD student at Columbia University and a student researcher at Google, and currently works on a wide range of machine learning projects, including reinforcement learning applied to HVAC systems, inferring neural network weights with only query access, and machine crystallography. But I'm assuming that today's talk will mainly focus on the HVAC.
Yes, you're correct.
So Judah, please share your screen and get started.
Sure. Hi, everyone. Thank you so much. I'm so happy to be here. Let me just share my screen. Hopefully now you all see my slides. Is that correct?
Yeah.
Fantastic. Okay. So I'm working with John, who just gave an excellent talk about, I guess, our wider efforts. So what I'm going to talk about today is kind of one focus within our project, which is designing a simulator for this process. So without further ado, let's begin. So I kind of divide this talk up. We'll see, I have 15 minutes to see how exactly this plays out, but I want to talk first about some of the challenges to bringing reinforcement learning to the real world. I think many people at this conference have already kind of touched on these points, but we'll go over them briefly. And then we're going to kind of, in reaction to that, discuss how we designed our simulator, how we calibrate our simulator, and maybe where we want to go in the future. And kind of just to talk about, I think John maybe touched on this a bit, but we have our goal of a 5% reduction here at Google, and this is kind of the impact we're hoping it will make just within Google. Obviously, if we can reach this goal, it will be enormous, not just for Google, but we all know buildings are about, I think, maybe 40% of energy use, so obviously very important. And yes, we are going to use reinforcement learning. Okay, so let's kind of dive into the details. Reinforcement learning on the real world has a lot of challenges. We all know these, so right, why can't we just train our agent on the real world directly? So it's too slow. Even the most sample efficient RL algorithms, if we were actually training on a real building, would take months to maybe even years to actually converge. So that's kind of prohibitive. It's expensive and it's dangerous. By dangerous, I mean that should the agent decide to go rogue or just explore lots of weird configurations, who knows what's going to happen. So obviously we can't train our agent in the real world. So as indicated by our friendly little robot playing in the sand, we need a safe training environment in order to train our agent. So what are the different ways of doing this? I know we've touched on some of these before. Let's go over them briefly. The first way, and this is indicated by a robot watching a child from a distance. I tried a lot of different diffusion images. This one was the least creepy. But the idea here, right, offline reinforcement learning directly from real data. And the idea here is maybe we don't actually need an interactive environment. Maybe we can just take several weeks or months of observations from our building and simply improve the policy directly from that. I remember earlier on this session, someone was talking about how they think this is actually the best approach. And while there certainly are merits to this, I think the merits are obviously that we can't, all the data is real, nothing is faked, nothing is simulated. But the limitation here is we're not going to be able to improve that much over our baseline policy because ultimately we're only limited from observations that were within the baseline. So that is one option. Option two, also touched upon earlier, is simply a learn model, right? An end-to-end learn model. This is an example of an LCM-based one. Obviously, there are many ways of doing this, but the pitfalls of a learn model are really it's not really physics-based. It's not necessarily grounded. So it may learn once again very well from the types of scenarios that are normally encountered in our baseline policy. But when we're trying to train an agent that's going to do lots of exploring on our learned dynamics model, well, our dynamics model probably never encountered weird things like just shutting off the boilers, right? So we may not generalize to strange state spaces that are nowhere near anything the baseline policy has seen. So simply having a learned dynamics model poses lots of risk. The third approach, and this is, we can call this maybe the energy plus approach, although I'm sure there are alternatives, is using a very high fidelity simulator. And so on the one hand, the pros here don't need to be said. It's physics-based. It should generalize well. It should be high accuracy. But the cons are, this is very difficult to configure, right? We're never going to know all the details. I think earlier was mentioned, is a window open or closed? But even more basic things like, if we want to scale reinforcement learning, if you want to scale HVAC control to a fleet of 1,000 buildings, we're never going to be able to customize the simulator to every building. We're not going to know the materials. We're not going to know, all the details of the structure. It's never going to be able to scale. And additionally, one could argue that even if we could scale this, we're still going to have the sim to real transfer issue. So maybe we're kind of putting our efforts into the wrong space. So the question is there a better way? We think the answer is yes, obviously, or there wouldn't be a talk. And so we kind of want to go somewhere in the middle. We want to basically develop the simplest possible simulator that is still useful. Okay, so the goal here is this simulator should be very, very easy to configure to a new building, right? And that's important because we want this to be able to scale. And yet at the same time, it needs to be useful, right? We can have a garbage simulator that scales very rapidly to new buildings, but doesn't actually generate any meaningful results. Obviously, that's kind of pointless. So our approach, kind of summarized in this very nice equation here, is we want to have a low fidelity simulator that's very simple, that can be configured very rapidly to any arbitrary building. We want to then combine that, tune that, configure that with real world data. And the balance, the trade-off will be, this should be easy to configure because it's not necessarily the highest fidelity, but because we're using real world data to increase its accuracy, to configure it, to tune it to the real world, it should be accurate enough to produce something useful. So kind of just to put this visually, you can think of it as there's a trade-off between fidelity and speed. Speed here can mean both actually the speed of running the simulator, but also just the speed in terms of how long it takes in terms of human labor to actually get the simulator up and running on a given building. So there's a trade-off. We can always put infinite time into the simulator, configure it perfectly, have lots of CPU cycles, and maybe the fidelity will go up. but the speed will go down, right? Or we could have a simulator that runs instantly, but the outputs are completely useless. So we want to kind of find the maybe we can call it the Goldilocks zone, the optimal trade-off between these two options, and hopefully we want to use data to kind of get us to the fidelity. So how do we go about doing this? So we're using a finite difference approximation. We basically divide up our floor plan into these small rectangular control volumes, and we discretize the time step. We're currently using 5-minute intervals, and we calculate this using a Taylor approximation. Happy to go into the details of this more. Maybe in the interest of time, I'm going to be a bit brief on this, but the key point I want to take away from here is this is pretty quick to calculate, but not particularly accurate. Okay, so you wouldn't want to be launching, launching things to space, so to speak, using these types of calculations. But the question is, can they be accurate enough with data? So let's talk about how we use data to make these kind of simple approximations more accurate. So this is an overview of our pipeline. And what's very cool is using this pipeline, we were actually able to have a single person, in this case happened to be me, configure our simulator to a building in under 3 hours. That means we took our pipeline, we took a new building, and we were able to get a simulator that was specified to this arbitrary new building in under 3 hours, which is quite rapid. This is the same building that John mentioned earlier. It has 2 stories, 197 devices. So it's not a massive building, but it's definitely not, something teeny. So we think that's a pretty good timeline in terms of configuration. And the way it works is we start off with a floor plan, as you can see in the leftmost image. We then extract the floor plan to a grid of control volumes, where you mentioned the control volumes over here, where we have a very rough approximation of the layout of the building, right? So each of these control volumes is, I believe, 20 centimeters. So it's not, the most granular, but we have a rough idea of the shapes of all the rooms. We also know which walls are interior and exterior. We then have a graphical user interface where a human labels all the devices, because the device locations are not found in the floor plans. So that basically just means you kind of have a list of devices and you match which devices in each room. Finally, once you've gone through that process, which I mentioned takes around 3 hours, we now have our configured simulator, and the final step is calibrating it to the real world using data, which I will go into now. And this is kind of, before I go into the calibration, this is kind of just a zoomed in view of what happens on the top. You can see our kind of messy floor plan, and we're able to go more or less automatically without any human input to the image on bottom using, using some computer vision techniques to smooth out the image, to kind of clean it out and figure out which walls are interior and exterior. So it's a pretty automated process. Now, we mentioned that these calculations that we're doing are not the most accurate. So I want to show you this video of what I mean by not the most accurate. So this is our simulator before we use real data to calibrate it. And what you see here, before I play the video, the image on the left are the 2 stories of our building in simulation. Image on the right are these 2 stories in the real world. And so what we're seeing here is before calibration. Red in this case means the simulator or the real world is hot. Blue and green means colder. As you can see, within about an hour, our simulator is already much, much colder than the real world. Which is not terribly surprising, because as I mentioned, our calculations are a bit simplistic, don't take everything into account. So it's not crazy that we would have significant drift if we don't perform any calibration. Okay, so how do we go about calibrating this? So, excuse me. In order to calibrate, there are kind of 2 requirements. We need a calibration metric, right? We need to know how good is our calibration. Are we doing well? Are we not doing well? Etc. And then we need some sort of optimization method to do better along that metric, right? Pretty straightforward. So our calibration metric is what we termed n-step prediction. Maybe it looks more complicated here than it really is. Let's go through it. We start with a set of n real-world observations. In this case, we took n to be, I believe it was 144. Each of these are 5 minutes, roughly 6 hours. And then we initiate the simulator to match the same as the initial conditions of the first observation. We then run the simulator for all of these steps. In our experiments, this was 6 hours total. And then after 6 hours have elapsed, we calculate the temperature error in every zone. So as you can see here, for each zone, we get the absolute error between what was observed in that zone in the real world, what was observed in the simulated world. We get the difference and we take the mean. Just to be clear, we are not calculating the error at every time step. We are only doing this after all n time steps have elapsed. Okay, so we're kind of seeing after 6 hours how much have we drifted. Now, we should also clarify that the amount of information we have in the real world is much more granular. Right? In the simulator, we know the exact temperature of every 10 centimeters, every control volume, of every 20 centimeters, excuse me. In the real world, we only know kind of one value per zone. So the zone in the simulator is just the average of all the control volumes in the zone. And then we compare that with the one value we get from the sensor in the real world. So that is our metric. And to improve this, we use hyperparameter tuning. So this is an example of a single run here. Here are all of our parameters. This is, I believe, 100 different runs. And we were able then to kind of improve the fidelity of our simulator. So these are the hyperparameters that we tune. Most of these are pretty self-explanatory physical constants. The one that's really not self-explanatory I'll talk about here is this. So our simulator does not actually take into account air convection. And so one way we've found of kind of very simply simulating this is with some random probability, we shuffle around control volumes within a single zone to represent the air from those control volumes moving around. So that this is kind of the one, I guess, non-physical property that we're also tuning. The rest of these are all physical properties. And here are the ranges we gave to our hyperparameter tuning and the best values that were found. What's interesting is most of these values are kind of physically plausible. They represent real materials, not necessarily are they always the materials we expect to find in buildings, but none of these values are too crazy. So that is kind of interesting as well. And let's look at briefly here at some of the results. So I should mention here that before we tuned the simulator, we had about an error of around 2.5 degrees Celsius after 6 hours. So we have here 3 different groups of data. We have our tuning data. This was the data that we used in our hyperparameter tuning process over here. We then had 2 sets of validation data. Validation data A was data taken from the same time of day, the same type of scenario that we tuned on, just a different day. And validation set B was a completely different scenario from what we were tuned on. As you can see here, while before we had any tuning, we had about a 2.5 degree error. After our hyperparameter tuning process, we only drifted on average 0.63 degrees from the real world over a 6 hour period. When we were within the validation data set A, which was, as I said, kind of a more similar scenario, and roughly 1.2 degrees drift in validation set B, which was a different time of day and different scenario. So far, pretty solid results. Obviously, the question still remains: is this good enough? Which is, I think, something we're still trying to figure out. But one thing we also did as well is we tried to analyze where are the errors. Why are we doing worse? Why are we not, getting a lower error? So we have over here. Let me explain this video. This is going to be a heat map that represents the difference between our simulator and the real world over a 3 hour period. So white is going to mean that, right, initially the simulator and the real world are initialized to the exact same configuration. So white represents there is 0 error between them. Red is going to mean the simulator was hotter in this case, and blue is going to mean it was colder. And we're also going to, it's a bit small to see on my screen. We're also going to show you these numbers are going to represent the zones with the biggest error and with the biggest positive error and the biggest negative error. So let me kind of play this video. You can see here, over time, we are drifting further and further. One thing to take away, well, I guess let me let it play first. Yeah, so one thing to take away, let me play this again. Maybe I'll make it a bit, the playback speed a bit slower. So one thing you can see here is we are actually have a lot of blue around the edges of the building and more red on the inside. And what that means is around the edges, our simulator is actually too cold, but it's a bit too warm in the middle, which gives us a bit of an idea of the errors that we're facing. It seems that our exchange with the outside is not quite up to par. And at the same time, the exchange within our building is a bit too slow. So that is kind of room for improvement. And then one other visual I'd like to show is this. So this is a visualization of our temperature drift over 6 hours. So, excuse me, over on validation set A, which was, as I mentioned before, validation set A was same time of day, different day. So kind of similar data to what we've tuned on, but on a different time period, a different day. And as we can see the drift over here. So let me explain what this means. Each of these are box plots representing the distribution of temperatures. We mentioned we have 127 different temperature sensors in our building. And so as you can see initially at time step 0, the simulator, which is in blue, and the simulator, which is in brown, and the real building in blue, have the exact same temperature distribution because they're initialized to be the same. And over time, the simulator is getting a bit warmer, and the distribution of simulated temperatures is also getting a bit narrower. So this gives us a bit of an idea of kind of the errors that we're facing and how to further improve our simulation beyond this. So that's what I want to talk about today. Thank you all for listening. Please ask me any questions. And I have over here kind of an overview of our pipeline so that if anyone has any questions, they can easily pinpoint to what was unclear. So thank you very much, and please ask away.
Okay, thanks, Judah. Let's indeed have some questions if there's any. Apparently, I don't see any raised hands yet, or unless I'm mistaken. Okay, Martin, you had a question?
Yeah, a very nice talk. Thanks for presenting it, and love the animation and the approach that you're taking. I was wondering, based on your experience working with the real building, and this is really the first instance I've seen something like this, so that's great to see. If you were to have a different building, how much of this changes? And just walk us through that process just to get us a
Yeah, absolutely. So if we had a real building, we would go through this process from scratch. So we would start off, ideally, we would be provided with the floor plans of this real building, right? So step 1 would be to run these floor plans through our processing pipeline, which should result in 1 image per floor that looks like this. Hopefully, this should be a pretty smooth process. Obviously, if the blueprints that were provided look drastically different to the ones that we designed this process for, it might not be as smooth. But ideally, pretty much automatically, without any real human input, we should be able to go from floor plans to a clean image like this for every floor. Okay? Once we had that, this image actually directly corresponds to our simulator's layout. Each pixel in this image is a control volume. Right? So imagine each control volume is 20 centimeters. Obviously, that can also be tweaked as well, but each pixel here is a control volume. So once we have this image, we then would need a human to tell us in this new building, where are the HVAC devices located, right? Where we want a list of every single temperature sensor. We want to know what room in this image is each sensor in. The reason why we need that information is because if we want to, have this perfectly mimic the real building, right? We need to know where everything is. So that kind of is the longer part of this onboarding process. I mentioned it took me, that was the part that took about 3 hours for 2 floors because it's just a bit, kind of manual labor of just clicking, this is here, this is there, but it shouldn't be too bad for an arbitrary building. So now once we have our floor plan with the locations of devices for our new building, we would then really need to do the tuning from scratch, which I think may have been your question, right? The hyperparameter tuning that we did on our building, we don't expect that to translate to a new building. The thought process is we may want to do kind of independent training for every single building. So ideally, we would have, on this new building, maybe 2-3 weeks of data. And then we would use that to hyperparameter tune from scratch to this new building. Does that answer your question?
Yes, thank you so much.
Sure.
Yeah, again, I see that. Okay, no, the question. Yeah, Mohammed still had a question, but I'm afraid we don't have time since we're running really late. We should have already finished according to the original scheme. So let's thank Judah again and move to the next speaker. The next speaker would be David Wolfle. I think he's still online and already sharing the screen. So you see the title of his talk there. David studied mechanical engineering in Karlsruhe, and during his master's in Flensburg and Kiel, he focused on wind energy technology. After that, so after graduating there, he worked as an R&D scientist in the industry, mostly on estimation and prediction of renewable energy power production. And in 2016, he has promoted to team manager responsible for software engineering and so product development and design and execution of project management. And now since 2018, he has been a research scientist at ZI Research Center for Information Technology, mostly on reinforcement learning. And he's particularly focused on automation, operation, and scalability of such RL algorithms. And so with that being said, David, please, the floor is yours. Let's get your talk started.
Thank you so much for the introduction, Chris. Okay, so the talk I'm going to give you today is called TBMNF, Environment to Assess the Accuracy of Thermal Building Models or Under Realistic Conditions. And I think it fits quite nicely to the talks that we have heard previously. So as usual, and as everyone before, I want to have a nice introduction. You know the drill. We have the energy transition. There are two major issues we have to face. One is the mismatch between production and demand from renewable energy sources, and the next one is that we have to increase energy efficiency to reach our climate goals worldwide, right? So we also know that buildings have a higher share, roughly a third, depending on the country, of final energy consumption, which makes them having a huge potential for increased efficiency and flexible consumption. So, but in Germany, we have roughly 21 million buildings. And the point is, if we want to have an impact on the energy transition, we need our systems to have or being deployed on a very large number of buildings. And that's basically the punchline for my research. I try to find methodology that works on a larger scale, right? So I want to have a short recap of optimization algorithms for building energy management too. I think like 6 years ago when I started this PhD position, most works were custom tailored for specific building, often using mixed integer linear programming, showed good results in practice, but were so expensive in engineering that were not viable in practice, right? So reinforcement learning has been emerged in recent years. It seems like it might be a good solution. I think it's not out there yet, but we're working on that. And I think that's also the goal of this workshop. One thing I would like to clarify here, because we had this issue about offline RL versus online RL. I personally think that if we, given that problem we have with buildings, that the data we observe is so low frequency, the approach to go to is model-based reinforcement learning. We can argue that later. I think we had it a bit during the keynote already, though. That's my personal perspective. I think model-based reinforcement learning is the most promising approach here, especially because it's the one that is most thermal efficient, or considered that way usually, right? Okay, so my point about it's not about introducing reinforcement learning algorithms for you. My point is about evaluation today. So the whole point is, how can we evaluate a reinforcement learning algorithm and show that it works well? And what we usually do in reinforcement learning is we let the agent interact with an environment and then report the average reward, for example, over the training time. So if we want to do that for buildings too, we can be lucky now. Then I think in recent years, several environments have been emerged, like for example, Bobtest or Synergem, that represent building energy optimization tasks. And this is now at hand. This is also different from the point I started my PhD, where we had no environments at all. So I'm very happy that those exist now. As a side note here, if you ever come to the situation where you need to select or even just evaluate which one of these environments you should use or not, then I would like to give you a recommendation about a paper from BuildSys, I think 3 years ago, which is called A Guide for the Design of Benchmark Environments for Building Energy Optimization, which is basically just tries to develop objective measures for, well, evaluating environments, right? Or how to develop them, but you could also use them to inspect or analyze existing environments and see what might be good for you and what not. Okay, but excuse my shameless amount of advertising for our own research. That's not the point here. I know these, or we do know that these environments are there, and we're thankful for them. But we have a little issue here if we do want to use those environments to evaluate our especially model-based reinforcement learning algorithms. And the point here is that what we usually want to do is we want to have an information if our algorithm will work well in practice, and in best case, if it will work well in practice on a very diverse and larger set of buildings. But the only thing we can do is we can interact with the environment. So we can choose an environment that represents some interesting buildings, or we can use several environments that hopefully represent a larger chunk of interesting buildings, but nevertheless, the models which we have in there will still be simplified. So we always have to encounter simplified physics in our environment, which basically means that if we see good performance of our MBRL algorithm interacting with the environment, we can safely conclude that the model of this algorithm is capable of learning the simplified dynamics. But that doesn't mean necessarily that the same model will work well in practice, because we've never checked if it's capable of learning true dynamics of true buildings. So that's the punchline basically of our paper, and that's something we want to, or the issue we want to address with that environment. So TBMenv is an environment to assess the accuracy of thermal building models under realistic conditions. So the most important point first is it's not a replacement. So it's not meant to be a replacement for BobTest or Synergym or any of the other ones, but it can be used additionally, and it should be used additionally. And if you have a look in how this environment works, we have like a classic import phrase. We do have here some lines of code where we do where we would train a model. In that case, it's a thermal building model. And then we have the very usual loop, which looks very close to what you know from gym environments. Apart from that, we do not expect our model to predict a action, but instead we want to have a prediction of future states. In that particular case, we want to have a prediction of the next 24 hours. Okay, so, and what we're going to do then is we're going to present these predictions to the environment. The environment will emit a new set of observations, actions, and disturbances. The model should take all of these and should then iterate and predict the next array of observations for the then next 24 hours. Okay, so it's just an ongoing process which iterates over time. And after we've all that done that, and the environment is finished or has reached the end of our data, we can use it to compute a performance measure. Performance measure here means mean average error of the temperature prediction. In that case, scenario 2, it's 24 hours ahead. It's the mean average error over 24 hours. And in that particular case, the thermal building model, which we evaluated here, was a persistence model, which is just means that this particular model has just forecasted the last value it had in its data and forecasted that value for the next 24 hours straight. So the score of that particular model is not very nice. It's 1.58 degrees Celsius mean average error. But it's just a minimal thing. So I think any model which you'd like to train, this is basically just an example of how the environment should be used. This particular model is, I think, the minimum thing. Any model you do must be strictly better than that one, because otherwise it's really not worth it to go any further, right? Okay. something about the scenarios and the baselines. We have implemented 2 scenarios. One is built on a 3-story office building on campus of a German university. You guess which one, I think. Scenario 2 represents an office building in tropical climate, that is in Australia. And we have not only implemented the scenarios and the logic to evaluate those, but also 2 baseline models. The baselines are considered, or should be, a strong baseline as reference to allow meaningful comparison of evaluation results. So it should be like something like a challenge to beat. I think that the baselines can be expected to demonstrate peak performance of non-machine learning models. So it's classic engineering models, which we know from MPC. And in particular, the model of scenario 1 is an RC model, which is quite popular in, I think, our domain. And the model for scenario 2 is a gray box model. And both of those have been specifically designed for the buildings that are represented by our scenarios. Furthermore, the parameters of both models have been tuned to achieve maximum predictive accuracy and to make it really a challenge to beat. And it's not shown here on the slide, but the mean average error of both models is around 0.4 degrees Celsius. On an average for, I think the one is 24 hours prediction, the other one should be 12-hour prediction horizon. Okay, so that gives me to my summary, or that leads me to my summary. I think the main point I wanted to show you today is that good performance of model-based reinforcement learning algorithms for building energy management on existing environments does not guarantee good performance in real buildings. And the issue is that simulation code is inevitably a simplified representation of reality. We have introduced the TBMNF today as an environment to assess the accuracy of thermal building models under hopefully more realistic conditions than with Energy Plus. And TBMNF that's the important point, is not a replacement, but something you might want to use additionally to get more insight about the expected generalization of your models. The task of TBMNF is to predict the zone temperatures recorded in 2 office buildings with AC systems, and we do provide 2 strong baselines for interpretation of model performance and as a challenge to beat. And finally, everything we've developed and all the data that has been used in our environments is open source on a GitHub page. So please go ahead, go there if you're interested, use it. That's what it's for. So thank you for it so much.
Okay, thank you, David. Please join me in thanking him. Nice presentation. I already see that Kevin raised his hand, so they should.
Sorry, I'm full of questions today. I find these topics very fascinating, and these presentations are really great. So thank you, David, for this one. This actually ties in with the previous presentation a little bit as well. So there are kind of 2 prediction tasks you can think of being useful from a model. And one is kind of given, say, the energy inputs or the control actions, the actuator positions, predict the evolution of the temperature profile. But the other one is, given the evolution of the temperature profile, sort of back out, invert the model to predict what the energy consumption would have been. So I guess I just want to say, is that on your radar, the sort of mapping from inputs, basically the actions that we take, to the important output, the energy or emissions or cost or whatever it is that on your radar as an important prediction task?
Not so much, to be honest. I think for my own research, it's not strictly necessary to have that information. I see there's a point for that, though. It kind of depends on how structured your model is, and if you, for example, try to learn or have enough information to learn, for example, the matching field of the, for example, heat pump, then it should be something similar, right? Or can be connected, but no. If you do work in that direction, or want to work in that direction, let's argue about this. But I won't have it on my schedule anytime soon.
Okay, makes sense. I have some stuff on this from a paper that came out, so I can send it your way. Do you want to maybe drop your email in chat for me? Thank you.
Sure.
Okay, then one final question for this talk and the session. Barton, you still have your hand raised, so I'm assuming you still have one.
Yeah, thanks, David, for a very nice talk. The question I was gonna go after was, like first I should clarify, I did not mean that offline RL is a solution to everything. Model-based and simulators all are going to play a role. I think it might be a combination of everything that gets us to scale. So for the evaluation strategy looks great to me. How do we think about evaluation when the agent is going to take some action that we do not know what it is, and we want to assess the impact of that on the model? Can the model do well in that unexplored space in the history? It's like, have you thought about evaluation criteria from that aspect?
No, I have not thought about how we can evaluate that particularly. I think the answer which we have to find is having a probabilistic model. And I think that's probably a solution for model-based reinforcement learning, that our models should yes, I do have thought about this. Now that I think about it, your question, I have to think, I did thought about it. I think the solution must be a probabilistic model. And I think the evaluation criteria must be if the uncertainty of that model, the estimated uncertainty, is correctly well represented with real observations. And you probably need to do something like training a model on some data, letting some algorithm interact in the real building, observe some new data, and then evaluate how well the uncertainty quantifications have been done or not. But other than that, I would like to say I love probabilistic models, but I think it's a huge challenge to get like a good probabilistic model. So that's my main work for, I don't know, 2 years now. It's not finished yet, but hope so anytime next year or so.
Thank you. That sounds great. That sounds close to offline to online as well. So there's some overlap there in the principles.
Yeah, I think so too. I think once you end up with offline RL and do it like really in a sophisticated way, you ended up like pretty close to model-based sometime, right? But appreciate the discussion. So I didn't want to bother you with the model-based too much before.
Okay, thank you guys for the discussion. I'm afraid I'll have to close the session because we're running really late now. So thanks again for the fruitful discussions. Let's keep in touch, and yeah, see you next time. I don't know whether the organizers have any final words.
Yeah, thank you, Chris, for chairing this session. Thank you, everyone, for showing up today, presenting all your awesome work. I enjoyed it a lot. It looks like there is more work to be done, so we'll see you at RLEM25, hopefully, next year. So this ends the paper sessions. And so for those who want to continue to delve into, we do have 2 tutorials in the breakout rooms that I just created. In the first one, I will call Bob Test. And in that one, David Blum and Javier will present Bob Test in a nice way. And in room 2, which I'll call now CityLearn, Kingsley will talk and then walk you through CityLearn, and you can enjoy it on Jupyter notebooks as well. So this should be open now. And so if you're interested, go ahead and join. And if you're not, thank you for your attention so far. Again, I enjoyed it very much. This ends our RLEM official part. Thank you. And the tutorials are open now. Thank you.
Thanks. See you next time. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.
Bye.
Hi, Zoltan, are you still there?
I am here, but I will jump off now. What's up?
Yeah, hi. I'm sorry, I just took off for a while, and I was just wondering, like, do we just have to move to the
Yeah,
other
you have
Zoom?
to. Yeah, you go either to the Bob test open room or the CityLearn room.
Oh, okay. Yeah, I can
For
see
the
the option.
tutorials. Yep.
Yeah, okay, awesome. Thanks a lot.